And out of curiosity, are there any songs that Ghana school children learn to sing other than the national anthem that like everybody would know?
There are a lot of songs, a lot of traditional songs. I don't think I even know up to quarter of them. So many in all the different indigenous languages.
Would you say that singing is, artistically, what would be like the biggest part of Ghanaian culture? Would it be singing or visual art or dance?
Generally in Ghana, it's singing and dancing. Because the two go together.
Yeah. Well, let's go ahead and get started. I'd like to welcome everybody back. I hope you enjoyed the first class. Seems that you've come back, so hopefully that's a good sign. Today we're going to discuss divisor counting. Well, that's going to be the first thing we discuss. We're going to discuss several things. And I saw that it looked like Wendy began discussing divisor counting with you guys yesterday. Is that right?
Yes.
So I don't know, I wasn't paying attention to exactly how she covered it. So I'm going to go ahead and take a look at it in my particular way because it does relate to other lessons that we'll talk about today. So let's start with the question, how many natural numbers are divisors of 180? And since you've already talked about divisor counting a little bit, what would be the first thing you'd want to do?
Prime factorization of 180.
Okay. What's the prime factorization of 180?
Two squared, 3 squared times 5 to the power 1.
Okay. Give me one moment. I'm going to adjust my screen here. Okay, so how does this prime factorization help us?
We can count the we can add the exponents together to get the number of divisors of 180.
Okay.
Multiply.
So there's a claim, and I'm going to ask, how do you know that claim is true?
Because of the fact that when you do multiply them and then you actually lay it out and sort of like do cases, you have with the powers of 2 or the powers of 3, and you actually go one by one and lay it all out, you see that that number is equivalent to what you would have if you were to multiply the divisors and add multiply the exponents with.
Yeah, so here I've laid out all the different divisors of 180, and I want this to be as intuitively clear as possible. And we can see that in this first column, I've got only 2 to the 0th power. All of these divisors have no powers of 2. And then in the second column, they all have 1 power of 2. And in the third column, they all have 2 powers of 2. And what we saw yesterday was if you have a divisor d of an integer, that it cannot have any more primes in the prime factorization, or any more copies of a prime in its prime factorization than we can divide out from the numerator. So we established that on Monday. So yeah, we can't have any more than 2 powers of 2, 2 powers of 3, and 1 power of 5, but we can have fewer. And so we go through the cases, 0, 1, and 2, and then powers of 3, 0, 1, and 2. And already we're up to 9 different divisors, but then we do the same thing with 5, 0 powers of 5, and 1 power of 5. And so for each prime, we have a multiplication process. I'm going to do something slightly different now. If we were to take this sum right here and multiply it by this sum right here and this sum right here. First of all, we have 3 terms, 3 terms, and 2 terms. So how many terms are we going to get in the product?
2, 3.
1.
So I'm going to ask the question a different way. Let's take a look at something algebraic. Suppose I multiplied x squared plus x plus 1 times y plus 1. How many terms would we get when we multiplied all this out?
Three.
Let's see. What if I multiply y? Sorry? What did the last person say?
I think you should use all as the person with an echo.
Okay. So what does the distributive property of multiplication tell us?
That your answer is the same no matter how you write it.
So here, I have distributed y plus 1 into 2 pieces, and I've multiplied each of those pieces by x squared plus x plus 1. Whoever it is who has their microphone on, we're getting a feedback. Go ahead and cut your mic.
I wonder if it's me.
So when we multiply these pieces, now we're multiplying x squared plus x plus 1 times y. And what do we get there?
X squared y plus x y plus y.
Right, we can now distribute x squared plus x plus 1 and multiply each of those pieces by y. And now let's look at the other part. We have x squared times 1 plus x times 1 plus 1 times 1. And now how many terms do we have?
6.
6.
Okay, now let's look back at the original multiplication problem here. When we multiply those together, how did we know we were going to get 6 terms?
You multiply the number of terms in each bracket together.
That's right. After we perform the distributive process over and over again, we're going to get 3 times 6 different pieces. Now, it may be that in some cases, some of those pieces will be like terms, and then we can combine those and simplify. But prior to that, we have 6 different terms. So now if I were to multiply a squared plus a plus 1 times b squared plus b plus 1, how many terms would we get?
9.
9.
That's correct. And now if I multiply that by c plus 1, how many terms would we get?
18.
18.
18. Okay, well that is the same number of terms we're going to get from this product right here. 3 terms times 3 terms times 2 terms is going to give us 18 terms. And let's look at what those terms are going to look like. 2 to the 0 times 3 to the 0 times 5 to the 0. Oh, look, that's right here. Then 2 to the 0 times 3 to the 0 times 5, times 2 to the 0 times 3 to the 0 times 5 to the first is going to be right here. What's going to happen when we multiply all of this out right here?
You're going to get exactly what you have up there.
Exactly. We're going to get exactly all of those divisors, each one of them exactly 1 time. So what is this product going to be equal to?
The number of divisors that 180 has.
The number of terms is the number of divisors, but then what are we doing with them?
The total sum of divisors.
Say again for me.
The total sum of divisors.
It'll give us the sum of the divisors, right? So if you were ever asked the question, what would be the sum of the divisors of an integer? This is what you could do. You could write out each of their primes to the power up to the greatest power in the prime factorization and multiply those together. The number of terms will be the number of divisors, and then the sum of all those divisors will simply be what we get here, and we can add that up. What is 2 to the first power plus 2 to the second power? Sorry, what is 2 to the 0 power plus 2 to the first plus 2 to the second?
7.
5.
7 is correct. And then what is 3 to the 0 plus 3 to the first plus 3 to the second?
13.
13.
And then 5 to the 0 plus 5 to the first?
6.
6.
Somebody want to compute that for me?
26.
546.
546. 7 times 13 is 91, and 91 times 6 is 546. And that would be the sum of all of these divisors up here: 1 plus 3 plus 9, 2, 6, and 18, 4, 12, and 36, 5, 15, 45, 10, 30, 90, plus 20, plus 60, plus 180. And does that seem easier than adding them all up ordinarily?
Yeah.
Yeah.
Yeah, it does.
Now, here's another thought is, what do these terms make up? Now, if I said, what kind of a series is 1 plus 3 plus 9?
The arithmetic sequence in its way, because you're adding. Well, not really.
So it's not arithmetic. What is an arithmetic sequence?
Constant
Like 2, 4, 6.
number. That's
It's a quadratic
It's like a-
sequence.
So an arithmetic sequence would be like 2, 7, 12, 17. It means that we have a first term, and then we add the same number to each term to get the next.
Yeah.
And then there's another type of sequence that we call geometric. And geometric might look something like this. Here's an example where we take each term and we multiply it by a common ratio. And we call it a common ratio because if we rewrite each term divided by the previous term, it gives us ratios. And these must all be equal in a geometric sequence. Now, what's the difference between a sequence and a series?
A sequence is constant with a constant coefficient, and a series can be random.
Not quite. I'm going to go ahead and, just so that you know the terminology, this won't be hard for you. It'll just be a matter of absorbing the terminology. Here's how the terminology works. A sequence is a word for, it's the mathematical word for a list. That right there is a sequence. That right there is a sequence. So if those are sequences, what is a series?
I'm not sure, but the list like ends, and I think a series does not end, like it can go on.
Not quite. A sequence can go on. You can have infinitely many terms in a sequence. But what separates a series is that it is a sum of the terms in a sequence. That would be a series. Or that would be a series. So let's, so I'm kind of, I'm stepping away from our regular curriculum today. You'll be able to read this later, and we'll come back, we'll work some of these problems. But let's talk about sequences and series and get to know them a little bit better, because we're very often dealing with sequences and series when we're working on number theory. A lot of our number theory relates to things that we need to do with sequences and series. So let's talk about...
Excuse me.
Yes.
Could you please repeat the definition of a series?
Yes, a series is the sum of the terms in a sequence.
Thank you.
So this first series, for instance, has a sum of 38. And this second one has a sum of 80. So let's talk about how it is first that we sum an arithmetic series. Let's suppose that we have this series, we'll do a simple one first. 1 plus 2 plus 3 plus 4, all the way up to 50. Let's say that we wanted to sum these. How could we do it? I mean, we could just add the 50 numbers together one by one, and then another, and then another.
Well, there's the equation, the n divided by 2. So the number of terms in the series divided by 2 times the first number plus the last number.
Okay, that formula works. And that formula will give you the 50th triangular number also. That formula works.
Excuse me.
Yes.
The person who just spoke, could you please repeat what you said?
I'm going to repeat it in different words now.
Okay.
I'm actually not worried about knowing the formula yet. I want to talk about the process first. So I'm going to steer the conversation in that direction. Let's say that you didn't know that formula and you needed to do this. Here's what I'm going to do. I'm going to start out, we've got this series. I'm going to give it a name. And I call this naming the beast. So we've named the beast, and I just called it S for sum. Now we don't just have a series, we have an equation. And sometimes it's easier to think about and work with an equation. And now I'm going to do something to this equation that relates to, who is it that gave me that formula? Was it Sneh?
Yes, please.
Okay, so Sneh gave us a formula, but I'm going to justify that formula. And I'm going to start by writing all the terms in backward order. Does anybody see how that helps us?
Yes, please, because by writing it backwards, we can pair them to get the same number each time.
Very good, Salon. Yeah, we now can look down each column and add the two terms in the column. 1 plus 50 is 51. 2 plus 49 is 51. 3 plus 48 is 51. 4 plus 47 is 51. Because the terms going down go down by the same amount that they go up in the other series, just a copy of the same one reversed, we get the same sums going down. And how many total terms do we have?
50.
25.
25.
50 terms,
Oh,
but then we've added them together, so we have 2 times the series sum. And that's when we can divide by 2. And I'm not even going to bother simplifying the way that I write. Actually, well, we'll go ahead and compute. What does that equal to?
127.
1,200.
1,275. So now this is a simple type of series, just starting at 1. And in fact, we call this a triangular number. And do you guys know why we call this a triangular number?
Because of the fact that the
Yes,
formula for the sum is the same formula for triangular numbers.
Yeah, if
No,
we're,
because if you arrange them in a form, they can form a triangle.
yeah, this right here would be the total number of dots would be 1 plus 2 plus 3 plus 4. And so the fourth triangular number is 10, 1 plus 2 plus 3 plus 4. And if we keep adding dots in a triangular pattern, we'll eventually get 50 dots down at a bottom layer. And if we ask the question, how many dots are there? There would be 1,275. So we call that the 50th triangular number. Sorry, I'm going to write that shorthand. Most people write it out in words. So now we have this method for summing a series, and the mathematician who came up with this regular technique was Carl Friedrich Gauss, who was the German mathematician who was responsible for, laying number theory on kind of solid grounding. He did a lot of the early research in number theory. And let's take a look at one more of these. Let's do a more complicated arithmetic series. Let's say that we were adding -8 plus -2 plus 4 plus 10 all the way up to 160. And this is an arithmetic series. We can see that each term is 6 greater than the previous term. And how do we get started?
We can start by trying to find out whether when you pair them, they would still give you the same number each time, to find out whether we should go forward with it.
Let's do something even before that. We're going to do that for sure. Let's do something right before that. What was the first thing that we did with the series in the previous example?
Naming the beast.
Name the beast. Yeah, we have this thing that's a little bit unwieldy to deal with. So we give it a name. Maybe we call it S or X or something else. Now we have an equation. Now what can we do?
We flip it and pair.
And
Yeah, it always gives 152.
so with this problem, we have a little bit of a difficulty that we did not have with the last one. What is that?
We don't know the amount of terms.
Okay, we still need to discover the number of terms.
That's basically 160 plus.
We have this process that we repeat over and over again of adding 6 to -8. We have -8.
So you minus -8 from 160 and divide it by 6.
So now, how many terms do we have in our series?
28.
So let's be careful. We do not have 28 terms. And I want somebody to tell me why. What happened?
We took -8 as 0, so you must add 1 to it to get in 9.
Good. Very good, David. Yeah, we added 6 28 times. But we did. Hey, somebody go ahead and cut your mic so that we don't get that echo. So we have -8 and we add 6 28 times. That gives us 29 terms. So you've always got to pay attention to what does your variable mean. And here n was the number of common differences from the first term to the last. But that means that n plus 1 is the number of terms. So from our work above, we now know that 2s equals 29 times 152. So now s equals 29 times 152 divided by 2. And I'll go ahead and take a factor of 2 out of 152. And you all multiply this out, and I'll do the same, and we'll check each other.
$2,204.
Are we all in agreement?
Yes.
Yeah.
Good. That's correct. So this is a way to sum an arithmetic series. Name the beast, flip it around, count the terms. So now let's talk about geometric series. And again, I'm going to start with one that's relatively simple. But I've got 11 total terms in this series. I made it just big enough that it would be kind of irritating, and you'd have to worry about whether or not you made a mistake, because that's a lot of addition. We're more likely to make careless errors the more arithmetic work that we do. So we'd like some nice methodology for handling this. So we look at this, and we're going to do something that we did last time to get started.
We named the beast.
Let's name the beast. We'll call it S once again. And then I'm going to go ahead and share with you guys something that I like to do in problem solving. I'm going to put this at the very end of this document. I'm going to talk about my favorite investigative questions. Because whether you are a detective, a mathematician, a scientist, or an engineer, or anything like that, you're investigating, you're trying to discover things. And so along the way, I think that there are good questions that we can be deliberate about. A lot of them become natural and intuitive, and we should still sometimes just ask them out loud if we're not sure what to do next. I like to ask first, what's ugly about this equation or problem? And another way of saying what's ugly is, what's the obstacle? What's getting in our way? What's the barrier? And then my second question is, what's interesting or beautiful or useful about this thing? And then I ask, what can we do? And then I ask, and this last one, you know, this comes only when you're dealing with stuff at the edge of your knowledge, the edge of your understanding, but it's so basic, it's so fundamental that the further you go in mathematics, the more often you'll need to ask this question over and over again, which is, what is the definition of this thing that we're dealing with? And I think that if you make a habit of asking these questions when you approach hard problems, that you will find yourself thinking about them in a more and more organized way. So now let's go back up here and let's ask first, what's ugly about this? And we've kind of already answered that question once, but somebody tell me in your own words, what's difficult about this?
It's just, you know.
If we were to flip it around, we can't actually, you know, add it and get the same value each time, which stops us from using our previous method of flipping and pairing.
Okay, it's not like a previous method. I'm going to say even before that, there are a lot of terms. There are enough terms that it's an irritating process. But yes, you're right. We don't have the ability to use our previous pairing method. Pairing methods are great. We can use them a lot, but we can't find a way to use them all the time.
The difference between the numbers are not the same.
That's
like,
right.
The first, yeah.
Yeah, it's not arithmetic, so we can't use the same principle. So here, I'm going to ask the next question, which is, well, what's interesting about this? What's useful? What defines a geometric series?
There's a common ratio between each term.
That's right. And that could answer question 2 or question 4. That could be what's interesting. It could also be what is the definition. The definition itself is very often what's interesting. So we have this common ratio. Okay, so there's a relationship between the terms. Well, let's ask, what can we do with this equation to get a second equation that is a lot like the first? Last time
Times it by 2.
Did you say divide it by 2?
No, multiply by 2.
Multiply it by 2. Either one of these is good. Traditionally, we multiply by 2 is the way that we do this. Good. So if we multiply this equation by 2, we get 2 plus 4 plus 8 plus 16, all the way up to 2048. And then I'm going to write that right next to the original equation. And does it become clear what we're going to do with these two equations?
Divide by 2?
Not yet. Let's remember that the thing which is our obstacle, which is ugly, is lots of terms. How do we get rid of what's ugly using these equations?
You divide the first one. You divide 2s by s.
Well, that would just undo what we did to get here.
You subtract.
If we subtract them. On the left-hand side, we just get s, the series sum. But look at what happens to almost all of the terms.
Oh, they cancel out.
Yeah. That's why we multiplied the first equation by 2, was to get, we have 11 terms in both series, in both equations, and 10 of those terms are the same. And so when we subtract, they just vanish from the sum. And that's all we get. Nice, huh? Let's do a second example. let's say that we have the geometric series 1/6 plus 1/2 plus 3/2 plus 9/2 all the way up to 729 halves. Now, does this look irritating to add up?
Yeah.
Yeah.
Yeah, looks kind of irritating, but it's not going to be so bad. What's our first step?
Name the beast.
What's our second step?
Find what's interesting and the obstacle.
Okay, what's interesting about the series?
The ratios are the same. Each number is 3 times the one before it.
That's right. We have a common ratio of 3. How do we make use of that common ratio?
We multiply the terms by 3. Well, the terms that we see.
Yeah, we'll multiply the entire equation by 3, and that gives us a second equation that looks a whole lot like the first. And now what can we do?
Now they cancel out.
Cancel the
minus.
like terms. Well, we subtract and then cancel the like terms.
We subtract the equations, and that will cancel out almost all of the terms. And after not too long, we have an answer. So now that we've done this, let's generalize. Do you guys know what I mean by generalize?
Mr. Crawford,
Yes.
I have a question because every time we cancel the others out and we have to add what's left, and we have to add what's left, you change it to subtraction.
Yes. We subtracted in this case the second equation minus the first.
Oh, okay. Thank you.
Yeah, I kind of did it upside down from the previous. Forgive me if I don't always write things out the way that I would, in a nice textbook format. I do that in order to be quick. I may not write everything, in a standard way. My focus with you guys is on the processes, because I know that you are all already talented, and we can discuss, how it is that things look a little different. So now that we've done this, I would like for us to generalize the process. What does it mean to generalize?
Putting the values of the answers in the formula.
Non-Orly, can you repeat that? Can you put that into a different set of words, maybe?
Like you put the value of the answers you got, you put into the formula.
Okay, we are going to derive a formula. That's right. We're going to solve the problem generally. We're going to solve infinitely many problems at one time. And that requires us to state all the possible problems of summing a geometric series with some finite number of terms. So we're going to do that by stating a first term. We're going to let A equal the first term of the series, and then we're going to let R be the common ratio between the terms. And we're going to see what we get. Such a series looks like A plus, what's the second term?
A times R.
AR.
The third term?
AR
R,
A.
AR cubed,
AR.
AR to the fourth.
And then I'm going to let n equal the number of terms. If n is the number of terms, what is the very last term?
AR to the power of n minus 1.
Good. It takes n minus 1 common ratios to get from the first term to the nth term. That's one of those, again, we have to adjust by 1. We have to understand the process to know. So here we have this, and now our next step is to name the beast. And then what is our next step after that?
Find the obstacle.
Okay. Our
multiply
obstacle. Okay, somebody was about to say multiply, and this is how we're going to get around the obstacle. Multiply by?
R, by R.
Yeah, by R.
And you should be doing this on your own paper. This level of derivation is something that you should be able to, what you want to be able to do is teach your friend. If you can explain this to somebody else, that's when you know that you know it well enough to really make use of it. It's also good practice. If you can derive formulas like this, that will help lift your mathematical game to the level of like the group 1 students. So now we take these two and we subtract them. And we can see a lot of the terms are the same, and we'll cancel. And what remains is a r to the n minus a. And now, what do we do with this? What our goal is to get which variable?
S.
S. So we need to get S alone. How do we do that?
We can divide both sides. No, wait.
You can send the S out to the other side of the equal sign.
Okay, we could add S to both sides to move S over, but then we've got S on both sides. I want to just get S alone. Right now we have an S times R and we have an S alone.
I think we could divide through by R, which would make it no.
Could we factor S out?
You could move S
So we
to
could divide both sides by R.
So Snake had the right idea. So what Snake said is, let's factor out S. The left-hand side becomes S times R minus 1. Yeah, sometimes we isolate through factorization. And now S equals, and sometimes we factor out the A, and we say that S equals A times R to the n minus 1 divided by R minus 1. And now we have a formula for computing the sum of any finite geometric series, so long as the common ratio is not 1. But if the common ratio is 1, then it's simple anyway. Any questions about this? Any thoughts?
I remember when we were doing this in class in school, my teacher told me that there's also the 1 minus r version, which has to do with the value of r being less than or greater than 1. And he said that if it's greater than 1, then you would use the r minus 1, but if it was less, then you'd use 1 minus r.
Yeah, this will give you the value regardless of whether or not r is greater or less than 1. This will work. It just may be easier to compute it. if you multiply the numerator and denominator by -1, then it looks like that. And it doesn't matter to me which you use. In fact, what to me, the most important thing is the process that got us here. I'll share this with you. I almost never use this formula. I almost always use the process. And I do that with most things in mathematics. If I use a formula enough, I wind up knowing it by heart. But really and truly, I don't like to memorize too many things. I like to understand the process. That understanding will help me solve more problems, but also I can forget the formula and just derive it on the spot. Once you've derived this formula a few times, you tend to you derive it in a few seconds. And that's not a lot of time. So memorization takes up a lot of space in the brain, but processes stick with us and allow us to do many things. So, I don't like to make up rules like, hey, if R is greater than or less than 1, do it one way or the other. But you can play around with it and do things as you like. And in fact, that process of playing around and doing it as you like is part of how you learn to make mathematics useful. So now,
Okay.
we've gone down this path. Now we're going to do something that looks much more intimidating. We are going to sum an infinite series. And we're going to start with the series 1/2 plus 1/4 plus 1/8. And we're not going to stop. We're going to have 1 over 1024, 1 over 2048. We're going to keep going. 1 over 1,048,576. That'll be the 20th term. And then we're going to keep going after that. We're never going to stop. And I would like all of you to think about this and work on this for a moment. I'm going to get me another cup of coffee while you work. So somebody tell me, how might we get started?
We can start by defining the last number, which would be 1 over 1. Wait.
Well,
I think
we
we
do
should
have
name the beast.
I like name the beast. Good, Don Gnarly. So one thing to mention is we do not have a last term, but we do have a general term. Each of our terms looks like 1 over 2 to the nth power. But we're going to name the beast right here. Now I'm going to go off on a tangent. And let's say that Non-Gnarly has a bow and an arrow. And does somebody want to volunteer to be brave enough to stand with an apple on their head on the other side?
I think I will.
Sure.
Okay.
Okay, I think David volunteered first, maybe. And so here's, some people put the apple on their head. Have you heard that story?
Yeah.
Yeah, look.
Okay, David's even braver than that. David's just going to make himself a target. He's just going to stand there and say, ha ha, you can't shoot me with the arrow. And Non-Gnarly says, why not? And the claim that David makes is that the arrow is never going to reach him. It can't reach him because there is some distance that it must travel between the two of them. And in order to travel that distance, it must travel halfway there, and then half of that remaining distance, and then half of that remaining distance, and half of that remaining distance. And it must do that infinitely many times. So it's never going to complete the process. So is David's theory correct?
So yeah, sort of.
Yes. You
Yes.
can't reach a whole number.
So are any of you willing to volunteer to have an arrow shot at you?
Yes.
Yes.
You better not be. You know, if I said that you were going to travel from Ghana to Togo, is it true that you would never get there? Because you have to travel halfway and then halfway again and halfway again?
Well, you'd get so close that you'd consider it there. Like, for example, how it is with 0.9 repeating, it's considered 1 because of how close it is.
That's one way of saying it, because of how close it is. And I would say that closeness is distance
Okay,
0.
so I don't think you would get there because once you travel half, you have to travel another half. But then again, you won't travel the half. So in total, you keep on traveling 3/4.
Yeah, these distances are going to get squeezed in there. But let's be reasonable. It's nonsense to say that if somebody shoots an arrow at you, it's never going to get there. It's nonsense to say that if you travel to Togo, that you can never get there. In fact, at least one of you lived in Togo, as we discussed before class. So obviously, you traveled from one place to another. So what's going on here? It messes with our minds a little bit to have this idea proposed this way. But here's the thing. Not only are the distances being cut in half, the time intervals are also being cut in half. And so they happen quicker and quicker and quicker. And it's important to remember something does happen. Everything that you ever do could be chopped into tinier and tinier intervals, but it does happen. So this is how we know, that we don't have to worry about whether or not an infinite sum, can have one number as we sum it. We call this convergence. This sum of this series, and we can begin to watch it converge. We can say the first partial sum is 1/2, and the second partial sum is 1/2 plus 1/4, which is 3/4. What's the third partial sum?
3/8.
More than 3/8. We're already up to 3/4 in the second partial sum, and it's bigger than that.
Seven.
And I'm just going to write it this way. I'm just going to add the new terms to the old. Oops.
$31 out of 32.
That's right. And we can see that these are getting closer and closer to 1. The remaining distance is being cut in half as we go. So after infinitely many steps, I claim that we get all the way there. And let's see how that happens. So we're going to, and this is called convergence. Convergence is when we get all the way there. So let's see how that happens. So we have the beast, to which we've given a name. And you know what? Let's just do what we did before. What did we do with this equation when we had a finite geometric series?
We multiplied all of the terms by the ratio.
We multiply by the common ratio, and that gives us a second equation, and it looks a lot like the first. Now what can we do?
We could subtract the
Cancel the subtract and cancel the term.
We subtract the second series from the first, and on the left-hand side, we just get 1/2 s. But what happens on the right-hand side?
You are left with the half, which is also known as, also the ratio, minus whatever the final term you could reach times half is.
Other than 1/2, every other term exists in both series. And so they subtract out from one another and cancel each other out, and all that remains is the first term. So the sum of the infinite geometric series is just 1. So moral of the story is, it would be unwise for David to stand in front of the arrow. So don't play that game. So now that we've done this once, can we generalize?
Yeah.
So
But I have a question though. What if the geometric sequence isn't in fractions? Like what if it's 2 4 1 2 4 6 8 1 2 4 8 16 32 like that?
So convergence doesn't always happen. Convergence only happens if your common ratio is between -1 and 1. If
Okay.
it's too big, the sum is just going to grow and grow and grow infinitely, either positive or negative, depending on your first term. If it's equal to 1, it's just adding the same thing over and over infinitely many times, and so that can go to infinity. If it's -1, then it might be like 3 plus -3 plus 3 plus -3 plus 3 plus -3. And the partial sums go back and forth, right? If you just add one term, your sum is 3. If you add 2, it's 0. If you add 3 terms, it's 3. If you add 4 terms, it's 0. So you don't have a definite sum. And if your common ratio is like -2, then maybe you have 1 plus -2 plus 4 plus -8. And if you look at those partial sums, they go back and forth, positive and negative, but the distance from 0, the magnitude of them, grows and grows and grows toward infinity. So the only time this really works, that we get convergence, is when your common ratio is between -1 and 1, or something special happens, like all your terms are just 0. And then it doesn't really matter what you multiply by as your common ratio. So
Please, can you go to the page before this one?
go back to the page before. You want to take a look at that again?
Is it possible for us to do like another example quickly?
Yeah, we'll do one more example and then we'll generalize.
Thank you.
You're welcome. So let's say that we start with 6 plus 2 plus 2/3 plus 2/9. Go on and on forever. Anahita, how do we get started?
First we name the beast. Should I keep going or?
Sure, go ahead.
Okay, then we can find the common ratio.
And what is that?
that would be divided by 3. So 3, I guess. 1/3.
1/3. Good. How do we make use of that common ratio?
We multiply the s by 1/3.
And now what would you like to do?
We subtract, and then yeah, we can cancel out to have first and final terms.
What do we get on the right-hand side?
This is where I get a bit confused, which is why I asked to do another one.
Okay. Archie, what will we get on the right-hand side?
Wouldn't it be the remaining factor, the terms that we haven't canceled?
Okay, and what terms have not canceled?
6 and 2/27.
So I'm going to point out that 2/27 is also...
Wait, but it's gonna cancel that way. If we go on, yeah.
Are there any other terms that don't cancel?
I don't think so, no.
No, there are no other terms that don't cancel. Every one is there, just shifted over. And so all we get is that first term. And notice I didn't even complete the arithmetic yet on the left-hand side. I did that because I wanted to allude to what's going to happen next when we derive the formula. But Anahita, go ahead and tell me, what is S going to be equal to?
Okay, so we could move the 1 minus 1/3. So S would be equal to 6 over, yeah, that, okay. So wouldn't that be 18/2?
Yes.
9.
We reduce to 9. So I did this partially this way so that you could all see this right here. Because when we work this generally, it's going to look exactly like this, except that we're going to have variables that name the first term in the common ratio. And we can see the first term right here. And we can see the common ratio right there. Well, let's do this from the beginning. And we will let A be the first term and R be the common ratio. And we have A plus AR plus AR squared, on and on and on. And again, we're going to assume that the common ratio is between -1, and 1. That way we do have a converging infinite geometric series. So R is between -1 and 1. Non-gnarly, get us started.
And first, you name the beast.
We'll name the beast. We will call it S.
And second, you have to divide by R.
I want to call on somebody here who hasn't participated yet in these series. Shreya, can you tell us what we would do next with this equation? Are you with us, Shreya?
Sorry, my internet is bad.
That's okay.
It's breaking up.
Can you tell us what we would do with this equation?
One second.
I'm actually going to move it over a little bit. I'll rewrite it.
Mr. Crawford, I have a question.
Yes.
If it's a sum to infinity in the series, and we're trying to find the total of all the values up into infinity, doesn't that mean that we would? I mean, we said previously that with the draw arrow and everything that we wouldn't reach the number, but then how are we reaching the number by using our formula? And if it's really possible to close the distance between infinity and the first term to solve for that number.
So I'm saying with the arrow does reach the target. That's why you never want to stand in front of an arrow. You know, when we go back to our very first example of 1/2 plus 1/4 plus 1/8, if we keep going to infinity, if we say we have infinitely many of these terms, it does equal 1. There is no difference between it and 1. And that it takes a little while for that to sink in. You know, consider this, you know, a beginning exploration in infinity. And it takes a little while to come to grips with this, but it does equal 1 because, you know, we can see here when we subtract these off, there's nothing else that remains, and we just get 1/2 on the right-hand side. And so S does equal 1. And there will be, you know, you'll learn further in calculus more and more refined methods for examining what it means that the series is 1, what it means to have infinitely many terms. But for now, just, you know, consider in this example that we are talking about the arrow, and the arrow does get there, and that you can travel from your home to the border of Ghana to Togo, and you will get there. And you'll always go halfway first, and then halfway again, and that'll happen infinitely many times if you consider yourself moving on a continuous number line. And it's okay. We do wind up with the sum. It's not almost the same, it's exactly the same.
Okay, thank you.
You're welcome. So now somebody, Keshav, tell us what we can do with this equation.
We can times it by 2. Oh, no, divide it by 2.
We could multiply or divide by 2. I don't think you mean 2 in this case, though. That was our original equation.
Yeah.
Can I try?
I'm not really sure, but I think you have to divide or multiply, but I'm not sure the number.
So in the previous cases, in the first case, we hold on one second. Whoever's asking, let me explain this for Keshav. In the very first case, we multiplied by 1/2. In the second example, we multiplied by 1/3. And in this problem, A is our first term and R is our common ratio. So what do we multiply by? We want a second equation that looks a lot like the first. Yes, we multiply by
R.
That's right.
So you multiply by R.
That's right, R.
So these, I need to quickly leave. I'll come back in like 5 minutes.
Okay.
Thank you.
So now we have two equations that look a whole lot like each other. And now what's our next step? Rishid?
We can cancel out. We can, I think, subtract.
And what do we get on the right-hand side?
Well, the A cancels out, so it becomes A. So S minus SR equals A.
Yeah, the only thing that does not cancel on the right-hand side every term has a companion, even if we haven't written it yet. So now we need to manipulate this equation. Salorm, what can we do to manipulate this equation?
Well, first we have to factor out s from the left-hand side. Then afterwards, we bring the 1 minus r to the other side of the equation so that we have s on the left side and a over 1 minus r on the other side.
And there we go. We have a formula that will help us sum any infinite geometric series that converges to a sum, that has a sum. Again, this won't work if you go 2 plus 4 plus 8 plus 16. If you have a common ratio that's not between -1 and 1, this won't work. But for anything where you have like a fraction, where your common ratio is a fourth or 2/9 or anything like that, this formula will give you that answer. Any questions or thoughts about this?
I have a theory that in any case like this, your answer will just be your first term plus the plus 1 out of the common ratio.
So I think I know where this theory comes from. And I used to do this myself when I first learned how to sum infinite geometric series. I noticed that there were certain patterns. And, you know, if I were to say what's 1/3 plus 1/9 plus 1/27th, let's discuss a couple and see where it is that, what it is that you're noticing. But then I want to make sure that you understand that it's not always going to work. So if we were to say, what is 1/3 plus 1/9 plus 1/27, somebody either use the method that we've created or plug it into the formula above and tell me what you get.
You get 1/2 or 3/6.
That's correct. What if we sum 1/4 plus 1/16 plus 1/64?
You get 1/4. 1/3, sorry.
That's correct. Good. And here we get 1/4. So we can see that there is a pattern if the first term is just the common ratio. We see this simple pattern emerging. However, not every geometric series looks quite so simple. If we have the geometric series, I don't know, 1,000 over 3 plus 7,000 over 27 plus 49,000 over 243. What's our common ratio?
7/9.
7/9. So the first term divided by 1 minus our common ratio and this number comes out from this arithmetic that involves the first term in the common ratio, but it's not quite so easily predictable as some of the other geometric series that we've seen. So you will be able to see some patterns with some simple ones, and that's good. If you can spot some patterns, it helps build your intuition when working with these types of series and these types of problems. But don't put too much stock in that. You will see things that you haven't seen before, and you need to know how to handle the series. But it sounds like you were all getting this down, so we're good. So now let's talk about that. I didn't actually intend to talk about series today. The reason that we walked down this road is because right from the very get-go, we started talking about not only counting divisors, but adding them up. And when we were adding them up, we added these terms together right here. Now I want you to look at each one of those factors. 2 to the 0 plus 2 to the 1 plus 2 to the second. What type of series is that?
A geometric series.
It's a geometric series, right? Let's take a look at another example and why that matters to us. Let's say that we wanted to determine, I'm going to use this symbol right here. That's sigma, the Greek letter sigma. And we usually use sigma to mean sum. So what if I wanted the sum of the divisors of 200? Well, what's the first thing that we'd want to do with 200?
Kind
Look
Prime
for the prime
Factorization.
Okay, so we have 3 powers of 2 and 2 powers of 5. And how is it that let's say first, let's count the number of divisors. How many are there?
12.
12 is correct. We say 2 to the E1 power times 5 to the E2 power. Every one of our divisors has a prime factorization in this form where E1 can be 0, 1, 2, 3, and E2 can be 0, 1, 2. But if we want to add them together, we want to add together all the possible prime factorizations. But that's the same thing as this sum multiplied, this geometric series right here multiplied by this geometric series right here. And we can use our formula for a finite geometric series and rewrite each of these as 2 to the 4th power minus 1 over 2 minus 1. And 5 to the 3rd minus 1 over 5 minus 1. How did I get those? It's that formula right there. But our first term is just 1. If I add 2 to the 0 plus 2 to the 1st plus 2 to the 2nd all the way up to, I'll go up to 2 to the 7th power. Our first term is 1, so it's equal to 1 times the common ratio to the 7 plus 1 power minus 1 over 2 minus 1. Does everyone see that?
Yes.
Yes, please.
So to sum the different divisors, let's see if I've got that formula written out here. I thought I had it written out in this document. It's probably somewhere, but maybe we can find it later. In the meantime, we've learned a whole lot of theory here. Let's put this into practice. Let's do a little bit of problem solving. And let's start with problem number 5 on this page. Actually, no, let's go back. Let's talk about problem number 4. How many odd divisors are there of 6,552? What's the first thing we might do, even if we don't know what we're going to do yet in total?
Prime factorizing.
Prime
Prime
factorizing.
Yeah, let's find the prime factorization.
It's 2 cubed times 3 squared times 13 times 7.
Good, I got the same thing. So we don't just want to count the divisors now. We want to count the odd divisors. How does that change what we're doing?
Well, now we can't use any powers of 2 because then it's no longer odd since it can be evenly divided by 2. So we only look for the sum of divisors using the odd prime numbers there.
Very good. Yeah, ordinarily we would say, hey, there are 4 possible values for E1, 0, 1, 2, and 3. 3 values for E2, 2 values for E3, and 2 values for E4 that are possible. And we would say in total, there would be 4 times 3 times 2 times 2, 48 positive divisors of 6,552. But, and who is that speaking? Was that Salorm?
Yes, please.
So what Salorm says is, hey, we no longer can use any other value for E1 other than 0. An odd number has no powers of 2 in it. Yeah, these are equivalent statements. Odd number, prime factorization has no powers of 2. And so instead of 4 values, we just have 1. And so we multiply the number of ways we could fill in the remaining prime factorization. 3 possible values for E2 times 2 for E3 times 2 for E4. And that gives us 12 odd divisors. And I'm going to tell you a mistake I've seen some students of mine make when first looking at this problem. I've had some students compute the total number of divisors and then think half of them are odd. But that turns out to be wrong. Why, you know, what's a good way of realizing that that's not right?
One way is to realize no right is that this is not a simple list, so not necessarily are there all the values difference by 1. And also we're looking at divisors, not necessarily counting numbers. So you can't say all the divisors, half of them are even and half of them are odd.
That's right. Very well put, Salorm. You know, for instance, if I have the list 1, 2, 4, and 8, clearly only one of the 4 numbers is odd. So we can't always say half the numbers are even and half are odd. You know, it depends on the nature of the list and the relationship between the numbers that are in it. Nicely put. Okay, let's take a look at problem number 5. How can we get started?
Prime factorization.
What do we do? Sorry?
3 squared times
Squared
11.
times 11. And then you put the 99 outside. So 3 to the power of 198 times 11 to the power of 99.
Good. So how do we use the model for prime factorization? I want to write out a model, and then I want to compare the model to the problem at hand. What does every divisor of 99 to the 99th power look like?
It's going to contain at least a power of 3 that is greater than or equal to 0, but less than or equal to 198, and a power of 11 that is greater than or equal to 0 and less than or equal to 99.
Good. Okay. Well, how do we fit this to the question? The question is, how many of these divisors are perfect squares?
Well, we could start by comparing actual perfect squares and their prime factorization. And so like 3 squared, and then we look at the factorization, it's still 3 squared, but something like 4 squared, that's 2 to the power 4. 30 squared, that's 2 to the power something, and so on and so forth, and try to find a pattern.
I like this exploration. We're not sure what to do yet, so let's play with some examples and see what we notice pop up about those examples.
Well, so far from what you're writing, we can see that the exponents are all even.
Good. How do we know that that's necessarily going to be the case?
Well, we know that's going to be the case because of the fact
perfect
that
squares.
What about perfect squares? Somebody.
You have to like multiply them by itself, so the exponent will remain 2.
Right. And you can see the way I just did it. I put that exponent outside. We know that when we have an exponential to an exponential power, we multiply. So we're multiplying each of the exponents by 2. And so, well, that tells us that every perfect square has even exponents. But if you have a number with all even exponents, is it necessarily a perfect square? For instance, if I gave the prime factorization 2 to the 6th power times 3 to the 2nd times 5 to the 2nd, is that a perfect square?
it's not necessarily a perfect square, but it could be due to the fact that it has even powers.
So can you give me an example of one that is not a perfect square? Has a prime factorization with only even exponents, but is not a square. So we're trying to establish one-to-one correspondence. Does anybody know what that means?
No, I don't think so.
So we have two different things that we're counting, and we're trying to see if they're the same. On the one hand, we have numbers with prime factorizations with only even exponents. And on the other hand, we have perfect squares. We're trying to count perfect squares, and we'd like to know if we can count them by counting the numbers with prime factorizations with only even exponents, right? Because one of these is easier to do than the other. I'll say easier, and then harder to think about. This is why we establish one-to-one correspondences. If we can show that these are the same problem, then we can work the easier one to solve the harder one. Now, what we know is that every perfect square necessarily has all even exponents. So we know that any number in the right-hand list is also in the left-hand list. Now, what I'm asking is every number in the left-hand list in the right-hand list? And this one right here is, I can rewrite it as 3 squared times 3 to the first times 5 to the first squared. That's 120 squared. The number on the left is 14,400, and that's 120 squared. So if it has only even exponents, can I do what I just did right here and rewrite it as a square?
I'm pretty sure you can.
How do we know for sure?
Well, maybe if we test it, but we use variables, so we square a variable and try and break it down using prime factorization and see, and maybe then we can decide that whether it applies for all square numbers.
We can definitely, if we want to write a proof, we can definitely use variables. Our primes and our prime factorization can be P1, P2, P3. But I think that we can describe what's going on without the need for writing a complete proof. Right here, what we showed was if we took a prime factorization and squared it, that we were multiplying an even number in to each exponent. We were multiplying 2 into each exponent, creating the necessity that each exponent was an even number when we were done. Can you go backward with that process?
Well, if you square any prime factorization of any number, you're bound to find the prime factorization for the square of that number. So that would mean that if we do find the prime factorization of any number and square it, it would be even, because if you multiply odd against even, you would get even, and if you multiply even against even, you still get even.
That's true, but that's the direction that we already went. We showed that if we square a prime factorization, we'll have even exponents. If we take a perfect square, if we square the prime factorization of its square root, then we'll have only even exponents. But here's what I mean. All of these exponents, if we start with even exponents, how about we just factor out the 2 from those exponents? And now we've gone backward in the process. We've said if we have only even exponents, that we can rewrite it as a prime factorization squared. Because we can factor that 2 out of 6, 2, and 2 to get 3, 1, and 1. Does that make sense? Have I explained that well enough? Our goal is to say, you know,
Teacher, I don't understand. Teacher, I don't understand.
So if we have 2 to the 4th times 3 to the 4th times 5 squared, which is, well, we can rewrite that, and this is going from the left-hand side to the right-hand side. We can rewrite that as 2 squared times 3 squared times 5 to the 1st squared. We can we can undouble the exponents. So yes, if we have only even exponents, then we have a perfect square. So every number in the left-hand list is in the right-hand list, and every number in the right-hand list is in the left-hand list. So these are the same lists. So we can count the perfect squares by counting the number of ways to write prime factorizations out of these that have only even exponents. So in how many ways can we choose a value of E1 that is even?
Well, we could first say that in terms, since we can see that the exponents are a simple list, we can say half of the possible exponents will be even. But then there's the fact of 0, because you can have zeros. So you add 1 to whichever value you have for half of the exponents.
Good.
So if we were to, we would come up with 3 to the power of 100 times 11 to the power of 50.
So there are 100 possible values for E1, and how many possible values for E2?
50.
That's correct. So how many total perfect squares can we construct in this way?
5,000.
5,000. Very good. Okay, let's move on. So we're going to do something a little bit harder now. We're going to go backward in the divisor counting process. What I mean is, I want us to find integers with exactly 8 positive divisors, and in particular, name the smallest such integer. Can somebody give me one example of an integer with 8 positive divisors?
Two to the power of 7.
True. That's one example. 128 has exactly 8 positive divisors. What's another one?
54.
Good. 1 plus 1 times 3 plus 1 is 8. We can use the exponents. Good. So where are we going with this?
So we're looking at divisors of 8, and then we're looking at the one with the smallest value.
What do you mean we're looking at divisors of 8?
Because so far what we've been doing is that we are finding the divisors of 8, and we're looking at how those divisors of 8 can be put into exponential form to form positive integers.
Good. Yeah, our method for counting the number of divisors is to add 1 to each exponent and multiply. Well, that gives us a product of each exponent plus 1 is an integer that is at least 2 multiplied together. And there are 3 different ways that we can write 8 in that way. We can just have one number not multiplied by any others. That's just 8. Or we can have 2 numbers multiplied together, 4 times 2. Or we can have 3 of them multiplied together, 2 times 2 times 2. And these each give us a possible prime factorization, like a prime to the 7th power, or a prime to the 3rd power times a prime to the 1st, or 3 different primes all taken to the 1st power would give us 1 plus 1 times 1 plus 1 times 1 plus 1 number of divisors. So now we want the smallest possibility out of these. Well, there's infinitely many possibilities still. How do we get the smallest?
Well, the smallest would probably be the one with the least amount of exponential value. So we could say that the 3rd row, since the divisors of 8 in the 3rd row are smaller, we could say that in prime factorization, these might also be smaller.
So maybe we're going to be real careful here, though. There's no good rule sometimes. Now, the one on top, the smallest example is the one that we've already named, which is 2 to the 7th power, which is 128. And we can definitely do better. What's the smallest example of p cubed times q to the 1st?
2 raised to the power 3 times 3 raised to the power 1.
Right. We use the smallest prime to the biggest power. We always want to use small numbers as possible. And that's equal to 24. Well, what's the smallest possible value of p times q times r?
2, 3,
30.
and 5.
30.
And that's equal to 30. So it turns out to be the second one of these. And really and truly, there may be, for a problem like this, there may be some that you can discard pretty quickly because, the higher the power you get, the more that just dominates the multiplication process. But, really and truly, you just have to go through all the possibilities and eliminate them, compare them to each other. In this case, 2 extra powers of p wind up being less than the smallest possible value of r that we multiply into pq. Right? 2 squared is less than 5. So we'd rather put in 2 more powers of 2 than a power of 5 to keep the numbers as small as possible. So 24 is our answer here. Okay, so let's move on. We've spent a lot of time on divisor counting, and we've talked about divisor sums. And I'm going to let divisor products be a homework topic. This is one, try to self-study this on your own. I have a good worksheet here on the process that you can check with. But let's talk about base numbers. So now I want somebody to, I need to understand whether or not you've studied this in school. Is there anybody who has not studied how to rewrite integers in other number bases in school?
I remember learning about it, but I don't remember much. Like,
We didn't.
I remember.
Yeah,
I
same
know
for
what
me
it's
too.
about.
But we did modular, so that's
Okay. So that means this is something that we need to review. So let's start there. So let's talk about what it is that we do when we write a number in a base. And it's about organization. In fact, tons of things in mathematics are really just about good organization. How is it that you would organize all these dots to count them? This represents some integer, right? There's some integer number of these dots. But, we could begin to organize them by 4s. But even that's not as easy as if we organize by 4 fours, 4 fours, then the extra fours, and then whatever is left over at the end. Right? This number right here, if we add it up, 32 plus 32 plus 4 plus 4 plus 4, sorry, 16 plus 16 plus 4 plus 4 plus 4 plus 1. What is that number?
Okay. 45.
45. But here's the way we would write it in base 4. In base 4, we would say, hey, we have 2 times 4 squared plus 3 times 4 to the first plus 1 times 4 to the 0. And in shorthand, we would just say, hey, that's 2, 3, 1, base 4. Just like in base 10, we would group by tens, and we would say it's 4 times 10 to the first plus 5 times 10 to the 0 equals 45. And I'll go ahead and put that 10 there, even though we usually leave it off because 10 is our standard number base because we have 10 fingers and 10 toes. But it's the same number of dots. Same number of dots, just written in 2 different ways. We can organize by tens like we normally do, or we can organize by fours. And every time you have 4 of a group of 4s, you make a larger stack of 4s. Like if we had 4 of these right here, we'd go in a 3rd dimension. We'd stack these squares of 4s on top of each other until we had a 4 by 4 by 4 cube that would have 4 to the 3rd power dots in it. So is that clear? We can organize this in terms of any, now I'll go ahead and say, no, things can get tricky because some people try to do this with fractions, but I'll just say for any base greater than 1, any integer base greater than 1, we organize into powers of that base where each digit is less than the base. Why does each digit need to be less than the base?
So that the base can divide the number. Like there won't be any, the remainder mustn't be higher than the base so that the base can divide the number well.
We want there to be exactly one way to write each number in a base. And so what we want to do is always force organization to the largest level, right? Here, in the middle of these 3 pictures, even though they're the same number of dots, I only organized into first powers of 4, and there were 11 of those, and that was pretty ugly. We could say, hey, look, there are 11 times 4 to the first plus 1 times 4 to the 0, and that's true, but we'd like to get rid of this number that is 4 or greater. We want to group as many of those into larger groupings of 4. And so we say, hey, look, 11 is 2 times 4 plus 3, where 3 is the remainder when we divide 11 by 4. And so that's where 3 becomes the number of 4 to the first powers. And we take the 2 and we organize 2 groups of 4 by 4. And that gives us that next higher power digit. So yeah, if the digit were at least 4, we would carry over to a higher digit place. Yes?
I was wondering, from the way I'm seeing it, this is a bit like modular arithmetic, putting the numbers into a new different type of mode to see it. So I was wondering if I could still think of it that way and I'd still be able to work with bases, but I'd be thinking about it as mod.
So in modular arithmetic, we would only be concerned about this number right here, the remainder when we divide by the base. And so basically that would be like saying always look at the units digits. 45 has a remainder of 5 when divided by 10. 45 has a remainder of 1 when divided by 4. But base numbers tell a more complete story. So they're not the same thing, but there is a relationship, and that relationship happens at the units digit.
Okay, thank you.
Sure thing. And let's go through an example. Let's say that let's say that we want to convert numbers, and let's say that in Ghana, I don't know, what's something that that might be traded between two countries?
Cocoa.
Cocoa.
I didn't hear the example. Repeat.
Cocoa.
Cocoa. Okay. So let's say that we have cocoa beans, and do you spell this the same way we do? Oops. Do you spell this the same way we do here?
Yeah.
C-O-C-O-A. Okay. Let's say that we have some exact number of cocoa beans, and let's say that in Ghana, you use base 10, and you have 1,894 cocoa beans. But let's say they do something weird in Togo. For some reason, they count in eighths, and they do everything that way. And so you want to repack, right now in Ghana, you package things up into tins. Maybe 10 beans per bag, little bag, and 10 bags make up a sack. Still a pretty small sack, but 10 sacks make up, what's a bigger?
A box.
I'll just say a box, thank you. And 10 boxes make a crate, and so on. We could make bigger and bigger groups if we wanted. So how many cocoa beans in a box?
1,000.
1,000. Yeah, and so if we were to package this up, we might start by saying, hey, look, we're going to take those 1,894 beans, and we're going to put these first into bags, and we're going to have 4 left over. But we have 189 bags. And then we take those 189 bags, and we package as many of those as possible into sacks. And we have 9 bags left over. Now we have 18 sacks of beans, and we take those 18 sacks of beans, and we put 10 of them into one box, and we have 8 left over. And then we just have that one box, and we have 0 crates, 1 box. So this is a kind of a repeated division process. It's kind of like doing long division, 1 step at a time. So we have, in this case, 1 box, 8 sacks, 9 bags, and 4 beans. And that's where we get our digits, 1, 8, 9, 4. Okay, that makes sense. But now we've got to repackage them for Togo. Togo puts 8 beans in a bag, and they put 8 bags in a sack, and 8 sacks in a box, and 8 boxes in a crate. And they will not buy your beans if they're not packaged that way. and you want to sell your beans there so that you can make a profit. So, what is it that we need to do? We need to repackage. So we take these 1,894 beans and we say, how many full bags can we fill? That's the first question. How many full bags can we fill? What do we do to find that out?
We multiply the amount of beans required for one bag against the number of bags and make a set.
Or just divide 1,894 divided by 8.
Yeah, we need to divide the total number of beans to get the number of bags. What is 8 into 1,894?
I think like something like 236. Something like that.
Somebody help us check this value. I think that's right. I think we have 6 left over.
Yeah. It's 236, remainder 6.
Okay, so right now we have 236 bags and 6 beans left over. Okay, now we need to take those 236 bags and put as many of those into sacks as possible. How many sacks can we fill and how many bags are left over?
We have 29. We can make 29 bags with, I think,
4 left over.
With 4 bags.
Good.
4.
Now we have 29 sacks, 4 bags, and 6 beans left over. Okay, so we're going to take those sacks and we're going to fill as many boxes as possible. How many boxes can we fill?
3 boxes.
Yeah, with
and
5
5 left over. 5 bags left over.
Good. So instead of 29 sacks, we only have 5 sacks, but we have 3 boxes. So here's what we've got. We've got 3 boxes, and each box, how many beans in a box in Togo?
8. No.
3. Sorry,
8,
4.
8 to the power of 3. 8 beans in one bag. One sack has 8 squared beans. One box has 8 times that, 8 cubed beans. So in total, what we have are 3 boxes, which have 8 cubed beans. Then we have 5 sacks, which have 8 squared beans. We have 4 bags, which have 8 to the first beans. And then we have 6 leftover beans. So whereas you write the number, you write the number of boxes, sacks, bags, and beans. And this number of beans, you call it 1894. That's the decimal number system, that's base 10. But in Togo, they write the number as 3, 5, 4, 6. And we'll put a little 8 down there to tell us that that's base 8. They're counting in a different way than we are. I don't know, maybe they've only got 4 fingers on each hand. Maybe they can only count to 8 so easily. Is that true about people in Togo?
No, of course, absolutely.
No, it's not.
No, it's not. They have 10 fingers, but we'll pretend for the moment. We'll pretend that people in Togo just have 8 fingers, so they count differently.
Why are we multiplying if we're going to come out with the same number values? Why are we multiplying by 8 cubed and 8 squared if we're coming out with the same number values to represent our 1,884?
Just to explain, it's the same number of beans, right? We count that number of beans, we write it, we represent it as 1894. But if there were another group of people, or maybe aliens, if there were aliens that only had 4 fingers on each hand, maybe they would count by groups of 8. And maybe they would write this same number of beans as 3, 5, 4, 6. They would write it in terms of powers of 8, whereas we write it in terms of powers of 10.
So if we wanted to convert back to base 10, we would multiply using 8 times the 8 cubed times 3, 8 squared times 5 to get the original power of 10, base 10 number.
If I understand you correctly, that is right. And so what's easier? Is it easier to convert from base 8 to base 10, or is it easier to convert from base 10 to base 8?
From base 10 to base 8, because we're used to base 10.
We have base 10 in both methods, and we have base 8 in both methods. Did this take, we just converted from base 10 to base 8. Was that quick, or did it take a long time?
It took quite a bit of time.
It took quite a long time.
It took quite a long time.
It took quite a long time. But let's say that Togo sent us beans packaged in their way, and we had 3 sacks, 3 boxes, 5 sacks, 4 bags, and 6 beans. Would that take a long time to count?
No, because if we knew your number system, we could work it back.
Yeah, going one direction, going from base 10 to base 8, we had to divide a lot. We used division over and over and over again. But to go from base 8 to base 10, we get to use multiplication over and over and over again, right? All we're doing is calculating that. So let's take another example. Let's say that we receive a shipment of beans from Togo, and there are 4 boxes, 3 sacks, 7 bags, and 3 leftover beans. How many beans did we just receive from Togo?
Well, in equivalent to their system, it'd be 4 times 8 cubed plus 3 times 8 squared plus 7 times 8 plus 1 plus 3.
And this right here, 8 cubed is 512. 4 times that is 2048. 8 squared is 64 times 3 is 192. 7 times 8 is 56, and then 3 times 1. Then we add these, and we get 2240. Add that to 56 and to 3, and we get 2299.
Yeah.
Good. That didn't take long, did it?
Oh.
No, but it certainly took us a long time to package it up their way, right?
Yeah, with all the division and everything.
Yeah, and there's a lot that we do in number theory that revolves around the fact that multiplication is so much easier than division. Division requires unmultiplying one step at a time over and over and over again, and that can be tedious. And sometimes when we deal with base numbers, we have to do the tedious side of it. But so long as you understand the process, that's the important thing. The process is repackaging a number in terms of powers of a different base, not base 10, base 8, or base 3, or base 5. Are there any questions about this?
No.
So
please.
Next week, we will do some clever stuff with base numbers. We'll do some problem solving with it. But I have, within this packet, I have a number of different problems. Don't worry about the stuff at the end. When you get down to the stuff that says modeling with base numbers, skip that for now. We should discuss that on Monday because that'll take some serious effort and serious time. But you can study the base numbers practice problems and numbers that have digits that we're not even used to. Like what would, if we had aliens who had 6 fingers on each hand so that they counted in groups of 12, we wind up using digits like A and B to represent the digits 10 and 11, groupings of 10 and groupings of 11. So keep studying that, and if you need me to, ask a question on the message board, and I'll see if I can put together any video answers that are necessary.
Please, since tomorrow we are writing the test, will we come on Zoom?
Say again about coming on Zoom?
Tomorrow, since we are writing the test, are we supposed to come on Zoom?
Oh, no. When you're taking the test, you call it writing the test. Understood. When you're writing the test, just do that on your own. And I don't care how much time you spend. Tomorrow, I will send you around 20 problems that Wendy and I are coming up with. And you can work it at your own leisure. I would say try to spend 2 hours or so on the problems. If you solve, if you're able to solve them all quicker, great. That'll be difficult. But if you want to spend a 3rd hour or a 4th hour on the problems, that's fine. Some of them are going to be challenging. At the very end of the test, we're going to put some very hard problems. And so it may take more time if you think that more time will help you get those other solutions. And then we'll discuss solutions to the harder problems on Friday, I think, on the schedule. Is that right?
No. On Friday, it's office hours.
That's office hours, yeah. We'll discuss any of the hard problems that you're unable to solve. You can ask about those during office hours.
Sorry, go ahead.
Yeah, go ahead.
Okay, I just want to ask if we can also discuss things like the lessons we've had on Monday, Tuesday, and Wednesday, if we have questions from there.
Yes, you can.
Okay, thank you.
I have 2 questions. The first one is, will the test be on the 2 topics that we like on number theory and counting and probability, or just?
Yes, I will come up with some problems from 2 classes that I've taught this week, and Wendy will come up with problems from her 1 class, and we'll mix those together.
Okay. And my second question is, do we upload it to, like, once we're done, how do we upload it?
So I'll go ahead and say this. If you want, you can send me your answers in an email. Okay. And I will, actually that's a good idea. Go ahead and everyone send me your answers in an email, and I will record them in a spreadsheet. To be honest, I'm not, I'll record them and I'll see whether or not you got them right or wrong, and that'll help me keep track, and maybe that'll help me know, what it is that you've mastered completely. But to be honest, I'm not as concerned about that as the fact that if you work on problems, you're going to improve. And to me, that's the most important part, is that you just ask questions about anything that you didn't master immediately, so that we move forward. And that'll be my focus.
Mr. Crawford, I wanted to know whether this was open book or it's just sit down without our notes or anything and just go through the questions.
Any questions that you have, we'll discuss during office hours on Friday. Is that reasonable?
No, I was wondering if it's an open book test, like we can have our notes test.
I would say try to take the test without notes first, then send me your answers. Then, if you like, go back and try to solve the problems you couldn't the first time with your notes.
Okay.
Please, could you send us your email address so we know where to send the test to?
Oh, yes. Did you not get my first email earlier this week when I sent out the first document?
Okay. I'll use that one.
Yes, use that one. Is there anybody who did not get that email? Great. Then you all have my email address?
Yes.
Yeah.
Yep.
Yeah.
Okay.
Wait, this video will also be available to us, right?
I'm going to post this one online later today, yes.
Okay. Yeah, thanks.
Mr. Crawford, you said you recorded yesterday's class,
Yes.
but it wasn't confirmed if it's going to be posted on the channel.
Right. There was somebody who crashed the video and said something inappropriate, and because of that, either we have to find a way to cut that out of the video, or it's not going to be posted.
Okay, thank you.
Any other questions? Okay, well, I will see you all on Friday.
Thank you, Mr. Crawford.
you.
Enjoy the rest of your day.
You're welcome.
Thank
Thanks.
you. Bye.
Bye.